Um, Good evening, ladies and gents, everyone. I'm Lenka from Prague AI, and together with Jano from a Better AI Meetup, we are thrilled, really, to welcome you at our very first joint event, which brings together our communities for a special evening of Czech and Slovak inspiration, featuring two prominent figures of our respective AI scenes, Stanislav Fort and Vladimír Macko. Standa, is he around? He's around, he's just there. This event is happening within Days of AI, which have become the largest AI festival in the Czech Republic. This year we are hosting about 250 events across 36 locations, bringing together about 15,000 attendees, and thank you so much for joining us tonight. As you can tell from the large number of logos, it really is a collaborative effort of numerous organizations that work closely together to create the greatest possible impact. One of our partners is the Technology Incubation Program of the government agency Czech Invest, and they are just launching their new call for applications. So should you be early stage startup or needing access to capital and good know-how, make sure to check them out for more information. The call ends on the 9th of January, if I'm not mistaken. We would like to thank all our sponsors, large and small, global and local, without whom Days of AI would just basically be a wishful thinking. Oh, I completely forgot about this slide. Yes, well, we are super grateful for the moral support of other organizations, very high places, including our beloved President of the Czech Republic. The Czech National AI Platform brings you not only Days of AI, but also, as of this September, Czech AI, Česká AI, which is a comprehensive map of the Czech AI ecosystem. There are about 340 companies right now, about 100 research groups. More is to come. We shall add other stakeholders such as events and communities, study programs, and more. Needless to say, it will never be completely exhaustive, but we will do our very best to keep it as complete as possible. And should you be looking for various opportunities, be it partnerships, research, jobs, do check it out. It's great. And last but not least, I don't know what I did. Yeah, no, you will have to fix that.
Yeah.
Or somebody
Let's
will,
turn it
because
off.
I will not fix it. Last but not least, collaboration is really the absolute fundament of Days of AI and very much of this event. So I would love to thank the Kempelen Institute of the Intelligent Technologies. Where's Majka Bělíková? Over there, the First Lady of Slovak AI scene, and Innovatrix for joining us in our efforts to really show the potential of Central Europe and that it has a lot to offer to the world, really. And we hope you leave this event inspired with broadened horizons and some new friends for your future endeavors. Have a great time. Thank you.
Thank you. Thank you. Thank you very much, Lenka, and thanks to all the Prague AI team for letting us crash their party. They have been partying hard for, I think, 2 weeks now, so yeah, we will call an end to that, sorry. But, you know, every party has an end. I have to say, I admire the number of logos that you are able to show, because we have much fewer. But I will continue in this, proclamation of togetherness and friendship and cooperation, because today we are meeting here for the 17th time as a Better AI Meetup. And there's actually, for the first time, we are actually in Prague, which is always great. We've been to Brno, we've been to Bratislava, so this is the first city that doesn't start with Br. So for us it's special, and it's triply special actually, because just 2 weeks ago we celebrated the 107th anniversary of start of Czechoslovakia, which is why we still love visiting each other in their respective countries. We are also, on Monday, we are celebrating the the anniversary of Velvet Revolution, which actually allows us to freely exchange knowledge, among other super advantages. But free exchange of knowledge is one of the greatest ones. Not that we couldn't exchange knowledge before, but not freely. You know, it has been actually prosecuted, so it's not anymore, and we are happy for that. And you know, talking about anniversaries, the triple anniversary is the anniversary of Battery AI. It's been 5 years ago this month that we started, and I was actually standing in front of a totally empty auditorium because there were COVID restrictions still in place, so it was not really a fun way to moderate if you don't have you know people in the auditorium. So thank you all for coming. It's almost full here, so there are still you know a couple of places that we will fill up until the next time we're in Prague. And we've been able to do this with Kinit and with Innovatrix, and also with Slovaks AI, which is supporting Slovak Diaspora, which is something that we do in Prague. And there's very strong Slovak Diaspora in Prague, of course, and in Brno. That's why we're traveling slowly and surely towards west with the Battery AI meetup. And we are also supported by and now I think I haven't broken it, thankfully. We are also supported by LoRa, which is an initiative of the European Union that supports cooperation on the AI fronts among nations. And that's it. And let's start with actually our content. And before I just introduce the first speaker, there are some housekeeping notes. So we are taking questions, but we are taking questions at the very end of the show. So after the two presentations, you can post the questions by Slido even now. The code is #better_AI, so you can start asking whenever you see something interesting in the presentations, and we will come to it later at the end of the evening after the second presentation. Also, if you have any questions, we decided with Lenka you can also ask by raising your hand during the Q&A session. So we have a microphone and we can walk towards you. And now to the speakers. So our first speaker, he studied in Cambridge and he has a PhD from Stanford. And Stanislav Fort is now chief scientist at AIL. And because in English, his surname is read as Fort, he will be, of course, talking about security. So, and also robustness and interpretability of large-scale AI models. So please welcome Stanislav Fort. Okay.
My slides seem to be down there. Thank you very much. Okay, it's a great pleasure to be here in Prague, and it's a tremendous honor to be able to speak to such a large audience here in Next Hub. Last year, I was standing here at the back watching Rich Sutton speaking about his research and his groundbreaking achievements in the history of reinforcement learning in the past. So standing a year later on the same stage is very humbling. Thank you very much for the invitation. It's a great honor. Let me first introduce roughly what I've been working on and who I am. And I'll go through a history and the position of AI research we're at right now to kind of describe the enthusiasm and excitement I feel in the air right now to all of you that you might be probably sharing, given that you're here at the meetup and you perceive the state of the AI field like I do. Later in the second part of the talk, I'll go to more technical yet unpublished research results that you might enjoy seeing for the first time as well. And to close up, I'll give a ground up summary of what I've been trying to achieve in this talk as well. So my path to AI led through physics, and I'll be going back to that in the talk as well. In the past, I spent a lot of time at Stanford doing my PhD on interpretability and the theory of deep learning, so understanding how neural networks work. I spent some time at Anthropic, being one of the first people on the team building parts of Claude that now seem to be serving billions of people. But at the time, we were a small company of roughly 20 people when I joined, and so I got to touch everything from pre-training all the way to the shaping of the personality of the model on the far end. I spent some time at DeepMind working on security for Gemini. And eventually, this led me to my current job, which is a position of a chief scientist and a co-founder at a Czech-American research startup called ISLE, where we work on the boundary of AI and security. I would be happy to talk to you more about that offline later after the talk. So without further ado, let me speak about the security and robustness of large AI models. Let me first position kind of this moment in history, in the whole scene of artificial intelligence in its totality. So the birth of AI dates quite far back. In 1956, a group of 10 men decided to solve AI in 2 months. And within this 2-month period, which didn't seem that audacious at the time, the goal was to make machines use language. So that's a pretty big, bold thing that they were aiming to do 75 years ago within a 2-month kind of summer break period. Form abstractions and concepts, again, something that we've only achieved recently, and also improve themselves. Luckily or unfortunately, we're not there yet, even with the current research we're performing like as we speak right now. So a very bold the beginning of the field of AI. They were not entirely wrong. They just misunderstood how difficult the actual task would be, and the method they were using was not fit for the purpose. Luckily, 75 years later, 3/4 of a century later, we've basically achieved what they were dreaming of back in that fateful summer of 1956. And this moment in particular is very personally important for me, because in 2015, this scene is actually a year later, the system AlphaGo from DeepMind, a European AI research company, beat a human champion, a European champion specifically, in the game of Go, a very ancient board game, more difficult than chess in some respects, for its branching ratio is higher than chess, so it's harder to estimate the value of a position just by brute force search that computers used to use before. But in the late 2015, a European champion was beaten by this AlphaGo system, and this kicked me out of my complacency. At the time, I worked on black holes at Cambridge and was deciding to do a PhD in physics. And this moment marked to me my realization that we've essentially discovered magic, and then AI is becoming a reality, that deep neural networks are performing something that seems to be akin to an intuition, something machines shouldn't have been able to do for a long time. This cover of the very prestigious journal Nature is showing a Go piece in which the sky is reflecting. And to me, this is connecting to two great passions of my life. Theoretical physics, here represented by the Milky Way and the starry sky, and the Go piece characterizing the intelligence part of my set of interests. So current AI systems, I would claim, would have been AGIs of the past. If I showed you what GPT-5 does right now, 10 years ago, you certainly would proclaim this is AGI. And even until recently, there were articles claiming that machines would never be able to do this and that. And typically, within a year or so, these achievements have been conquered by publicly available systems. We were folding proteins, and there were Nobel Prizes for that already given last year or 2 years ago. Self-driving cars are reality. In San Francisco, I do not take human driving cars anymore. I just take self-driving cars all the time. Machines are solving mathematical problems on the frontier of pure math research, as testified to by Terence Stahl, one of the most famous mathematicians in the world right now. So we are at a stage that I would claim would have been called AGI 10 years ago or so. To me, this is an amazing moment in history. We've built a digital mind, I would say, and it was way easier than we thought. This is a very surprising moment for me. The only things that it took was a lot of computational power, so 10 to the 26 operations or so. For the more chemically or physically minded people in the audience, this is way more than a mole of particles. So this is a macroscopic amount of computation this took. It's a lot of computation. A decent parallel architecture, here being the transformer model that was discovered gradually, but the landmark paper is this attention is all you need paper right here, and roughly 100 million books worth of text to train on. All these things seem kind of as difficult milestones to clear, but realistically, a lot of compute, a lot of data, and a decent architecture are not kind of fundamental breakthroughs we might have imagined we would need to kind of get to that stage where we historically would have called the systems we have AGI. So very surprising to me. It was way easier than I would have predicted, and basically, everyone in the past was predicting. A very fundamental insight is that AIs are grown, not constructed. And this is very unusual for the engineering-minded people in the world, because its creators themselves do not understand how they function internally. Obviously, we do understand exactly how they work on the level of matrix multiplications and on the very lowest level of actually simulating the system on a digital computer. We know exactly what the system does. These things are absolutely transparent. We see exactly what's happening at every single step, and we could by hand simulate the whole process of thinking. But on the high level, why the system answers, a particular word, or why the code it writes is functioning or not, is a very mysterious aspect of the whole thing. And only very nascent a field of interpretability is trying to peer into the black box of deep neural networks and understand actually what's going on. The graph you see here is a model extracted from Claude by a research paper from Anthropic, trying to understand internally how this model actually adds these two numbers. It's a very complex mental map they extracted from the functioning of the model, but on the low level, it's a lot of matrix multiplications, but on the high level, very complex algorithms emerge during the course of training of these models that we do not understand, and neither do the creators of these models. So a very unusual situation. Unlike a steam engine, we have no idea what's going on inside these models. There is a famous quote by Richard Feynman, a very famous physicist and one of the scientific heroes of mine, which says, "What I cannot build, I do not understand." It turns out we could create this, and yet we also do not understand. It's not a contradiction. If you flip the implication, it's not contradicting that. But we are capable of creating systems, supervising the growth of systems that do perform amazingly well and are very useful, and yet our understanding of the internals of these systems is very limited. So what is my research on this? Well, my research is trying to build a principled understanding of AI using empirical methods, kind of coming from physics. This is the angle I'm using. And the goal of that research is to build interpretability, robustness, and security primarily. Now, let me jump into a more specific kind of down-to-earth problem that is easy to convey to you here in the few minutes I have, which is very central to the field of machine learning, which is how do I convey a human function locked into my brain to a machine in a reliable way? Here's a little graph for you. When you have a human brain and you're looking at a picture of a tortoise, somehow the photons from the tortoise, the bouncing of the shell and everything, go back to your brain, to the retina, they get converted into electrical impulses, and some magic happens internally that no one understands really. Neuroscience didn't really make much progress on that question. And something magical happens, and the symbol tortoise pops up in your brain, and suddenly you know what you're looking at. Through introspection, if you kind of think really hard, how do I know this is a tortoise? You basically cannot answer this question in a way that you could convey to a machine in a detailed enough way. You couldn't describe, a program that you could write in Python or C++ that would actually recognize tortoises in images provided to the program. So that's why it took a long time to solve image recognition. It took neural networks that are trained to do that, not programmed to do that, to be able to achieve that goal, even though it seems very simple on the surface for a human, because you know exactly what you're looking at if you look at that picture. I could look at a parrot, and the symbol parrot pops up in my head. I could look at a picture of Prague, and the symbol Prague, the semantic symbol Prague pops up in my head. So I do this somehow very efficiently, very fast, without thinking and without conscious introspection of what is actually happening in my brain. And obviously, there's an implicit function sitting in my brain, mapping the input images into the semantic labels in some way. Let's call it this F. And different humans likely have different functions, mapping images to the labels in slightly different ways, but humans typically agree on what they're seeing in the world. Like there's a large amount of alignment, and apart from a few optical illusions like the black, red, the gold dress that you might remember seeing online, we basically agree all the time on what the subject of the vision actually is. So how do we convey this to a machine? We collect a data set and take a bunch of examples of these classes and label them with specific labels, such as airplane, cat, bird, or what you have. And we send this data set to a computer, and using a training algorithm here, stochastic gradient descent typically, or variance of this, and a functional approximator that is called deep neural networks, we train this, and the machine develops its own function G, mapping images into labels. This is how it's always done in machine learning. And luckily, this function G works really well. We are good at seeing things, and so is the model. If you show the model a bunch of images of cats or dogs, it answers cat or dog very reliably. If you add noise to the pictures, the models are not tripped up by the noise. They're really, really robust to these inputs. They're sometimes even more robust than human vision system on its own. We can train them to be better at withstanding noise being added to the pictures. But unfortunately, these functions are not the same. And the whole point of this talk will be to show you how exactly not the same they are and how critical that dissimilarity is to the field of AI security. So how is this exactly connected to AI security, right? Like, why would I care whether the function the machine learns and the human learns are not exactly the same? Well, one task I want from a machine is judging a morality of a situation, and I'm conveying to the machine the morality or immorality of the judgment in exactly the same way I'm conveying the dogness or catness of an image to the machine. So when a human looks at a situation like this, for example, a trolley problem here, a famous philosophical kind of intuition pump that people use, you can make decisions, and humans typically agree on these. But a machine trained on a bunch of text and a bunch of books and a bunch of moral-like situations also makes a judgment and typically agrees with you as well. If you talk to GPT-5, you would not be surprised by the reactions of the model. It typically aligns with a bunch of kind of aggregate human judgments. But it turns out these functions are also fundamentally, critically not the same, and exactly at the points of the disagreement, the danger of these situations lie. My pitch is basically, if you cannot even solve the basic problem of making sure the functions mapping images of cats to cats and images of dogs to dogs is not kind of reliably the same as humans would predict, what is the chance the grander problem of actually conveying the moral intuitions to the model is reliably conveyed in a way that doesn't break under pressure? There is a potential solution called the scaling hypothesis that's been the dominant philosophical theme of AI research for the past, let's say, 5 years or so. In essence, this hypothesis says that everything in AI gets better as it gets bigger. And there are many results confirming exactly that. There's a famous paper here called Scaling Laws for Neural Language Models from the year 2020. Interestingly, I think super majority of the people on that list of authors are now dollar billionaires because they co-founded a bunch of companies based on the hypothesis and the insight that the bigger, the better, and therefore higher performance. And you might suggest that this is a solution to the problem, right? Like, I'll just make it bigger, and maybe it'll be more robust as well. And you would be right in basically every case. So this is my paper I was lucky to work with Jia Ren and Balaji Lakshmanarayanan, in which we show that as the models get bigger, they also get more robust. So this was a great news. And I assumed, okay, great, we'll just make them really big, and they'll be really robust, right? Like, this is a very obvious kind of continuation of the line of argument, and very, enticing thought. So is scale the solution? Well, it turns out it's sadly not the case. And I'll show you exactly how not the case it is in the rest of the talk. Let's play a simple game, and I now require a audience participation. So please do not feel shy and just shout when I ask what the answer to the question will be. It'll be very simple for you. What do you see in this image? All right. Well. And this image being shown to a small vision model, the model would agree with you. It's a 99.9% dog. So correct? Congratulations, you're as good as the machine in the picture. All right, what is this? All right. Well, I totally agree. A human visual system says it's still a dog. But unfortunately, if you present to the very same neural network this very picture, this slightly hued up picture of a dog with this rainbow patina on it, the model says it's a 99.9% car. And this is not a made-up number. I actually trained the model on a very small data set called CFAR10 recently, and this is the result you get. To a human, nothing basically has changed about the picture of the dog, right? Like, it's basically the same thing, very recognizably a dog. Here, for comparison, the original picture without the perturbation being added. So what actually happened here? Well, a specific kind of perturbation called adversarial attack was designed and added to the picture, perturbing the pixels really slightly. You can notice that there's the little rainbow hue across the dog. causing the model behavior to react as if this were a super stimulus of the shape of a car. And now the model doesn't even just see a car of any kind, it sees the most car-like car it has ever seen in its life. This is like the most super stimulus car you could ever imagine for the model. This is very surprising, and it's not surprising just for me, it's been surprising for a whole generation of people I'll show you later. It's a very specific mathematically crafted noise, and it's a kind of noise I spent the last few years thinking about pretty hard. And it's a big problem kind of sitting at the heart of all machine learning right now. These adversarial examples, as they're called, have been known since 2014. And here's a landmark paper called Explaining and Harnessing Adversarial Examples with pretty famous co-authors. Incidentally, the first author of this paper, Ian Goodfellow, is an angel investor in ISLE, my current startup. So he's also an author of a very famous machine learning textbook. And he laid out the foundation of this very fundamental problem at the heart of machine learning. And 10 years later, and 10,000 papers later, we don't have a solution. It's literally an unsolved problem. It's a very simple problem. You can demonstrate it easily in a small kind of toy setup on your desktop or laptop, and yet it hasn't been solved. And the same problem applies even to the largest models out there. This is a paper I co-wrote last year in which we demonstrated exactly that. And let me show you exactly what's going on here. Here's a video I would like to play. So maybe if people on the back end could play it. Let me see. Oh, sorry about that. Could I ask for the video to be played, please? OK, great. Thank you. All right, so this is me talking to a ChatGPT and asking, what do you see in this photo? And I'm adding a particular photo I made specifically for this. It's Stephen Hawking, as you can see. And I ask GPT-4o, what do you see? And look at what it says. So I made the picture look like the very famous meme video, Never Gonna Give You Up by Rick Astley. It's a very famous 1980s video that became a cultural staple. And I confused the model into seeing something else than Stephen Hawking, specifically the target I wanted, by choosing a small modification to the picture myself. This model has been trained with all the safety techniques we could imagine. It's worth, for sure, over $100 million. And yet, I could break it easily on my own computer with a bit of thinking and a little bit of compute, roughly 1 cent worth of compute. And so it's a very asymmetric situation, and it shows very clearly that the problem of adversarial attacks isn't limited to only small toy-scale models, but it also applies to the biggest systems in the world, such as GPT-4. And even the largest models are susceptible to these attacks, and I'll show you some results from a new unpublished paper of mine where I show kind of specifics of this issue. Here's a picture of a, could I ask? All right, yes. And if you ask GPT-4o, it says it's a panda, right? Like it's clearly a panda. And I guess you can see the direction I'm going to. But if I add a very small perturbation here, magnify it to kind of look like more visually pleasing to you, but it's actually very small, and I add it to that picture here. When you ask the model what it sees, it says it sees a gibbon. Right, so it's very surprising. Something went wrong with the model, and I wonder, is it something alien? Like, if I asked the model to visualize what it saw, would it be some like just gibberish noise that just looks like a gibbon to the model? But no, when you ask the model to draw what it sees, it actually draws a very nice gibbon. So the human sees a panda, the machine sees a gibbon. Yes? So that's a valuable, it's a valid hypothesis. It's not as simple as you describe it. Like no one basically adding a little bit of like image on top, but very subtle in a way that doesn't confuse the human, but it's very powerfully confusing for the model. So it's a very well designed, kind of like specifically crafted image, but not exactly against GPT-4o, because obviously I couldn't get access to the model myself. I made a picture that now works for every single model out there, starting from the smallest ones all the way to the largest ones at the same time without having access to them individually. So this is kind of confusing for all machine learning models in the world at the same time, and it's not confusing to humans, showing a fundamental difference between the way humans perceive the world and machines perceive the world. So, robots see this very nice gibbon. Here's a really great example. I can subtract a concept as well from the picture. Here I take a panda, apply this little choice, little noise on top. Now the panda looks a bit kind of rainbowish, but if you ask what the model sees, it doesn't see a panda, it sees a bunch of people praying on a rug. Surprising, right? Well, let me show you one more. Here's a great article showing that these models are extremely good at telling where a photo was taken. So here's a picture of the MIT dome, correctly localized to be at MIT. Here's a small modified version of it where the model thinks it's at Oxford. So it's a very, I shifted the picture from a correct location in Boston all the way to Oxford, UK, by applying a very small modification targeted to confuse the model very specifically. Here's a picture of the University of Cambridge, King's College Chapel, which I made, in sequence to appear to be Princeton, Harvard, and Svata Barbara in Kutná Hora. So these models, despite their amazing robustness, are extremely easy to sway with a targeted attack in a way that's very inhuman to a human observer. Here's a really interesting case of self-driving. Look, here's a traffic light, right? You see it in the picture. Now, an attack picture here, nothing to a human has changed. If you ask what the traffic light is showing, the model says green, despite the thing being actually red. And if you ask it if it were a self-driving car, if it would go through the intersection, it would say yes, and it would just be confused about what it's seeing, despite the picture not really changing to a human observer at all. Here's another picture. Here's a question of hiding a traffic light. So you see the traffic light in this original scene right here, right? You see it on the right-hand side. It's there. And the machine says yes, but on the one here, the machine says it doesn't see a traffic light at all in a very similar scene to a human. So what's going on here? Well, I applied a very small perturbation on top of the region of the image with a traffic light. To a human, the perception doesn't differ at all. Yet to the machine, if you ask it to recreate what it sees in that picture, it recreates a detailed scene of Cambridge, even hallucinates the name Cambridge on the bus, but just completely omits the traffic light where it should have been. So I could hide it from the machine completely without damaging the rest of the screen of the scene with a very small perturbation being applied to the picture. So does reasoning help? It's one of the hypotheses that people have is that maybe if the model thinks longer, it'll be able to kind of figure out it doesn't see correctly and self-correct. Well, you could try 4.0, which is you could go from 4, but you could go to 0.4, which is a model specifically shown and advertised to be great at visual reasoning. And you could ask what it sees, and it would still be confused about the nature of the picture. It would still see, instead of Stephen Hawking, the very specific target object of the Never Gonna Give You Up video by Rick Astley. So not even a small confusion, but a rather large, very directed confusion chosen by me to be funny. Well, so reasoning doesn't help, right? If you ask it to draw what it sees, it draws a very convincing Rick Astley in some kind of gothic background with a microphone and everything. So it obviously doesn't perceive correctly the way we would assume the model should. So it goes further, though. Getting these artifacts to work in the physical world used to be really difficult. This is a adversarial turtle, a paper from the deep past of the machine learning, where a team from MIT designed a turtle with a little bit of rainbow patina applied to it to look like a rifle to a bunch of easy, small visual classifiers of the time. And since then, it's been assumed that the scale of these new models basically made this impossible, until we actually produced a working example very recently. So here's a picture of the Hawking I was showing you before, printed on a photographic paper by me, and obscured by a bunch of things, such as a Waymo sticker and a mug of mine on my desk. If you ask the model what it sees, it doesn't see Stephen Hawking, it says Rick Astley, so that's pretty great. And you could ask it to recreate the scene it sees in his head, and what you would see is that it actually correctly draws the sticker and the mug, but very nicely the Rick Astley picture pops up from the background. So this is a very robust perturbation, surviving being printed and obscured in a bunch of ways. Another example, here's a turtle, rubber, and scissors on it, and yet, it sees a very nice Rick Astley singing to the microphone here. You shouldn't walk away with the impression that this only works for Rick Astley. It's a very specific perturbation, but you could apply anything you want to it. And here's another one, a book, sunglasses, and my DeepMind bag, and then it still sees Rick Astley there, singing while the rest of the scene is undamaged. And here, a very strong glare, very strong orientation, and yet the visual effect of the perturbation is retained. So very surprising. So we actually managed to produce these adversarial perturbations that survive being printed, survive the physical medium, and survive all the transformations that you get by taking a picture of it with your camera. And I actually made these into my business card recently. Here's a bunch of them on my keyboard. And if you ask about this picture and ask what a model sees, this is GPT-4o again, it sees a bunch of pictures of the Never Gonna Give You Up video by Rick Astley. So this really survives a lot of transformations. This fooling of the model is extremely robust, very prevalent, and basically every model from the smallest to the largest is attacked in the same way. And yet, this doesn't transfer to humans at all. Very surprising, and fundamentally this demonstrates really clearly and visually that machines see very differently than humans, and therefore the conveying of the visual function from me to the machine failed completely in these edge cases that I could easily find and exploit. So what is my chance of actually conveying the alignment and moral intuitions in a much more complicated and open-ended situation? And the same applies to language, by the way. Let me just give you a really quick glimpse of what's going on in the language case. You could kind of look at a simple question like this and ask, what is 1 + 2? And the model would obviously say the answer is 3, right? So this is correct. But in this recent paper of mine that I presented this year at ICLR in Singapore in the spring, I could apply a small perturbation to the kind of the thought or the activation of the first token here, very small perturbation, and I could modify only 25 parameters out of 1,000 specifying that one activation, and yet I could sway the word being presented by the model as the next token in the sequence to be turtle, which I've chosen to kind of match the theme of the talk. But if you give me access to the full vector specifying the token here, I could do way more. I could make it recite specifically a long poem word for word as an answer instead of answering correctly. So these perturbations being targeted and swaying the model's decision to a particular outcome are realizable in language as well as vision. So every modality is attackable in a very similar way, showing the fundamental brittleness of these systems. Very surprising, right? So it's all connected to high-dimensional geometry, which happens to be the theme of my PhD thesis. And I'm very happy I've worked on it. This is the thesis of mine in the middle. And it's a very active area of research. But as I said, 10,000 papers later and 10 years later, no solution is in sight. So I think this could be a call to action for all of you. I think a lot of you have research ambitions, and you should kind of look at this problem and see whether you could kind of make a headway here. So well, I think it's a very open and the right problem for a solution. And fundamentally, I view this as a problem, which is a toy version of the broader AGI alignment question. We're actively pursuing it right now, so if you're interested, talk to me. And just really briefly, recently I've co-launched a new research startup on the boundary of AI and security called ISLE. And we're actively working on problems kind of in the neighborhood of what I've been presenting here. Not exactly the same, but kind of touching on it. And if you're interested in that specifically, please speak with me later. We've got a world-class team of engineers and researchers sitting right here in Prague. So it's a very enticing opportunity. We're working on extremely fundamental problems on the very edge of what's known in AI and security. And I think we're making a tremendous progress, primarily thanks to the amazing team we have here. So speak with me later. All right, thank you very much, and this will be all for me.
Thank you. Okay, yes. Thank you, Standa, for your talk. It's been very interesting. I think it was I think it has to be like one of the most massive physical recalls I have ever seen in my life. So we will. I think we all know what we'll be playing in our heads, once we finish here. But let's continue with the basically totally opposite side of the technology. Instead of like really all-encompassing recalls and stuff and pandas and cats and everything, we'll go to hardware and mathematical specifics. And now I will invite Vladimír Macko to show us how to make large language models really small, but still work as if they were large. Something that you might come across in your areas of applications. So Vladimír is the co-founder of consultancy GrizzlyTech, which actually helps companies compress their LLMs without losing function. And Vlado, please welcome.
Hello, ladies and gentlemen. I'm very happy to stand here right now. It's actually my second time in Prague this year talking about these things. Out of curiosity, please just raise hands if you already seen my talk earlier this year. Okay, nice, a few people. Good. This one will be very similar, but bear with me, we will go into much more bloody details regarding GPUs and some low-level stuff and matrix multiplication. So brace yourself, especially for the second part of the talk. For the rest, I promise it will be still understandable, all will be well. So let's do this. I will be talking about LLMs, about some compression of LLMs, how to make them smaller, and about some properties of modern GPUs with no prior knowledge required. You probably noticed that we are living in a bit of an age of LLMs. In recent years, we had all these amazing tools, ChatGPT, Claude, Grok. But more importantly, we also had some open source variants that were also open weights, like Llama or DeepSeek. Unfortunately, these models are either behind closed APIs and you cannot really play with them very well, or even the open source versions have like billions of parameters and require tens or hundreds of GPUs to run comfortably. Well, I don't have hundreds of GPUs. Maybe show of hands, who has like access to hundreds of GPUs? Oh, nice, okay. Very good. You should talk to those guys if you want. So here is Jeff Dean. Jeff Dean is head of AI at Google, and he has access to millions, probably, of GPUs. And he was asking these questions like, why can't you just run these models on consumer hardware? Well, who knows? So it's kind of hard for these large players to emphasize with us, either in academia or like smaller industries. So we cannot accept them to help us, so we need to help ourselves. And that's where we come in. Me and my colleague Vladimír, we are doing research at Comenius University and then applying this research through consultancy GrizzlyTech. I have background in large-scale ML training. I worked in Google AI briefly for DeepMind. I worked for a company that's doing privacy-preserving biometric authentication. But most importantly, I want to run those models on small consumer hardware. So let's first see what we actually want to run. So this is Llama 270B. It's older model, but it will serve us very well for the sake of this talk. And we see that it's kind of nothing special. At top, there is the embedding layer, which is pretty much a lookup table. Then we have a bunch of linear layers. We repeat it a bunch of times, and we are done. Yeah, exactly, right? So this is a 70 billion parameter model in float point 16, which means that you need 140 gigabytes of disk space to store it, or of GPU memory to run it. That is either two H100s or some similar hardware. That costs roughly $50,000 to buy, if there is like no craze for GPUs right now, or $3,000 per month to rent. That's quite a lot. In advance. Oh, well, depends, but yeah. With committed usage for 5 years, or I don't know. And if you don't have that type of money, or you just don't want to spend it, let's gracefully assume that you have access to this RTX 5090, which is like one of the highest-end consumer GPUs, costs $3,000 to buy, $300 to rent. Let's look at what you actually have at your hand, and let's see like what the GPU actually is. There are two main parts of the GPU. One is the memory that stores the data that the GPU need, and second is called streaming multiprocessors, or SMs, and those are cores of the GPU that are actually performing the computation. And these two things also have attributes that are most commonly, I guess, advertised with GPUs, and that's the GPU memory size, how much data it can store, and it's the speed in which it can do computation, so how much teraflops it can do. For this GPU, it's 32 gigabytes of memory and 105 teraflops. However, these streaming multiprocessors are not connected directly to the global memory. And for them to access data, the data needs to go through multiple levels of caches. First is L2 cache, that is relatively small compared to the global memory, only 98 megabytes. And then finally, an L1 cache, which is even smaller, only 128 kilobytes, but each SM has one cache on their own. And the speed at which the data goes through these levels is not instantaneous, but it takes a while. And it's captured by an attribute called memory bandwidth, which I would argue is actually much more important for a lot of use cases, but much, much, much less advertised. You may ask a sensible question, but what about the speed of transfer between the layers, like between the L1 cache and L2 cache, or L1 cache and SM? And it turns out that we don't really know. Like, NVIDIA does not really advertise these numbers at all, and the only way how to find them out is to either measure them yourselves, or wait for a bunch of researchers to measure them, first find out how to measure them properly, then measure them, and then publish an academic paper about that, which I think recently, around a month ago, actually came up for this GPU. So if you're interested, look up for it. Also importantly, the GPU is usually plugged into some computer and can also access data in the host memory of the computer. However, this connection is usually much, much, much slower than the rest of the numbers that you see there, and takes like 3 times more than the memory bandwidth. So if you want to read something from the host memory, it takes 4 times as much as if you want to read something from the global memory. And this is pretty much the main reason why, if you are running some machine learning, you really, really want your model to fit into the global memory. Okay, let's see again what we are trying to fit into the global memory. So here again is the Llama 270B. At top we have the input layer, or we have the input tokens. Then we have a matrix that's representing the Q, K, V, and O projections. Then we have attention. And finally, we have a matrix that's representing the MLP and a bunch of up and down projections. And then repeat this 80 times. Finally, we get the result. How to make this smaller? What can we even do about this? So first, I guess most obvious technique is called distillation. What it does is that we take the architecture of the model and we downscale it in all possible imaginable ways. So first, we replace the 80 repeating blocks by 40. We downscale it from 8,000 to 5,000. Second most popular method is called quantization. And what we can do is that we just take the parameters of the model, and instead of representing them as 18-bit floating point numbers, we represent them in less bits, either 8 floating point, 8 FP8, int 8, or int 4. The problem with quantization is that we don't really have that many options into what we can quantize. We can quantize it to 8 bits and get a 70 GB model with perplexity 3.17, which, funnily enough, there's almost no reduction in perplexity, or like no degradation in perplexity when we apply 8-bit quantization. Or we can go down to 4-bit and get perplexity 3.2. However, if you want to go below 4-bit, it gets very hard and very complicated, and we still cannot fit that model into our GPU memory. Gracefully, or luckily, Meta provided us with a bunch of pre-trained distilled versions of Llama. One Llama 13B that has 26 GB of memory, but has a significant reduction in performance. And perplexity goes to 4.57. Or Llama 7B, and the perplexity is even worse. But we see that there is a bit of a gap, that this model only uses 26 GB of memory, and we still have like some room on our GPU. So we would like to have some method that is somewhere in between. Something that's flexible, where there is not much performance degradation, and something that we can run locally on our GPUs. Because running distillation is pretty much infeasible in reasonable environment, because the cost for that is almost as big or as bad as running on training the full model. However, when we tinker with the weights of LLM, we need to be very careful about this effect, or about this phenomena, called superweights in large language models. And it turns out that these models have sets of weights that are extremely important for the model to work correctly. And if you mess these weights in a bad way, the model completely breaks. So let's illustrate it. If you take Mistral 7b and ask it to complete a sentence language modeling is, it happily completes it as it's the most fundamental and basic task of machine learning. I mean, a bit opinionated, but that's a good answer, right? Then, if you run this one line of code and set 1 out of those 7 billion weights to 0, the model completely breaks. And all of a sudden, it thinks that language modeling is not like not dot as good dash without if that dot. Like, no, I don't think anybody would find that as a sensible answer. And this tells us that if we are removing the weights or changing them, we need to be very careful about which ones we are removing, or at least we need to adjust the rest to compensate accordingly. And that's exactly what we are doing. The research and applications that we are interested in are mainly based on a technique called neural network pruning, which does exactly that. You take an architecture and you try to remove some of the weights from it by setting them to 0. And the work is mainly based on 2 papers, one by Vladimír Macko, called Fast and Effective Weight Update for Pruned Large Language Models, and second, a simple and effective pruning approach for LLMs. The first one is also called WANDA. Okay, now if you don't like math, please close your eyes and I will tell you when to open them. Just listen to my explanation. It will be okay. So what we do to make this problem feasible is that we divide it into a sequence of layer-wise problems, and we'll prune the network 1 layer at a time. And how we do this? We take a very small set of calibration data, feed it through the network, and record the activations and activation magnitudes for all the weights or all the neurons. Then it turns out that based on this information, you can very well remove the least important weights from the model. And based on our research, or based on Vlad's research, it turns out that updating the rest of the weights is actually a convex problem that could be solved by convex optimizer like ADMM. ADMM gives you an update rule for how to update the rest of the weights, and we iterate this process. So we take the layer, remove some weights, update the rest, remove some weights, update the rest, remove some weights, update the rest, until we reach the desired sparsity that we are interested in. And let's see how it works and how it performs. These, again, are perplexities. Lower number is better, best number is in bold, and we see that all the bold numbers are in the ADMM row, so hooray, great academic success. Unfortunately, in practice, it does not help us that much, because you are still better off using the small distilled version of the model than the one that's already pruned. So, I mean, good for a paper, but not good for a practice. How can we push it further? It turns out that if you replace 1 matrix by 2 matrices and increase the depth of the network, it actually performs better. And that's actually what we did in this paper. Again, if you don't like math, close your eyes. Oh, I forgot to tell you to open them. So nobody needs to close their eyes, perfect. So what we do is that we are trying to look for 2 matrices, A and B, that reconstruct the original weight matrix the best possible. Again, it turns out that if you fix one of those matrices, finding the second one is a problem that can be optimized by a very similar algorithm that we did before. So we do that. We fix A, optimize B, fix B, optimize A, fix A, optimize B, and so on, until we reach desired sparsity or performance or whatever we are interested in. How does it perform? Again, perplexities, best numbers are in bold, all bold numbers are in our row, so hooray, academic success. However, there is also a very nice practical success, because it turns out that if you take Llama 13b and prune it down to 50%, you will get a model that's actually better than the distilled version of that model, which to our knowledge is like one of the first methods that actually achieves this for pruning. Unfortunately, when you look at 70b model and prune it down by 70%, the accuracy is comparable to the 13b model, but the pruned version is unfortunately much larger, but you don't see it in the slide, so like whatever. We are getting in a good direction, but there is still some room to go and some room for improvement. Luckily, this translates to other domains as well. And even better, it turns out that if you're in a visual domain and have problem like ImageNet classification, you can take the ResNet model and remove 90% of its weights, or set it to 0, without much performance degradation. So your model size goes down to 10%, but there is only 1.6 drop in accuracy, which is pretty surprising to me. Okay, all pictures taken, good. How can we push this further? It turns out that you get the best results when you combine pruning with quantization. So what can we do is that we can take the 70B model, originally 140 gigabytes, apply double sparse factorization, or pruning, and 4-bit quantization, and we end up with a pruned model that only has 26 gigabytes, which is comparable to the original Llama 13B, but the pruned model actually has much, much better perplexity than the distilled version of it. And all of a sudden, you can take this model, and you can deploy it on your GPU. And in the end of the day, you can save like $2,600 per month, or 87% of compute. If you are OK with the fact that the perplexity went from 3.12 to 3.76. OK, how can we push this further? Can we somehow push this further? Turns out it can, but first we will need to understand some more fundamental things about GPUs. The GPU does two things. It moves memory, and it performs computation. And if you take these two numbers and you divide them, you will get a quantity called ops per byte, which is 58 for this 5090 GPU. Important thing is that you can do the same for the algorithm that you want to run on the GPU. For example, FP16 inference, which is pretty much matrix multiplication with bit size 1. And if you do this for this matrix vector multiplication, it turns out that this algorithm requires 1 operation per byte, which is much less than 58 operations that your GPU is capable of. And that means that this algorithm is memory bound on your GPU. What that means is that if you do fewer operations in this algorithm, it will not necessarily get faster. But if you reduce the size of memory that you need to work with, it gets faster. In other words, if you get a GPU that has more teraflops, it will not help you at all. But if you get a GPU that has faster memory, it can help you significantly. Let's have a practical example. Let's see how it works on Llama 213B inference on 2 different GPUs. One is the 5090, and 7 is like the recently announced DGX Spark that I guess you can already buy. The first one is a consumer GPU. The second one is kind of hailed as this AI future for personal inference. So first, the computation. For this inference, we need to do roughly 26 gigaflop, or gigafloating point operations. And on this GPU, it takes us 0.2 milliseconds, so almost nothing. However, we need to get that data from memory to those SMs. And on this GPU, with 1.79 terabyte per second transfer speed, it takes 14.5 milliseconds. Because these operations can run in parallel, the whole computation takes 14.5 milliseconds and results in 68 tokens per second, which is quite good. It's slightly above average human typing speed. Now let's look at this future of AI machine. It advertises a whopping 1 petaflop per second. We will ignore the fact that this is int4 operations and like give it some slack and assume that this is FP16 or whatever. And it can compute those things in almost no time, 0.02 milliseconds. However, this machine has memory bandwidth of 0.27 terabytes per second, which means that the memory transfer will take us 96 milliseconds. Again, the whole operation will take us 96 milliseconds, and we will end up with a horrible generation speed of 10 tokens per second, which is something that one would not expect based on NVIDIA marketing materials. And it's always good to kind of check it manually based on what exact load you want to run. Good. Something that I have not told you strategically is how do you actually use sparse matrices in practice? And it turns out, like, okay, we reduce the size, but what then? It turns out that the best use of sparse matrices in practice is just to reduce the memory so you can fit into the global GPU memory, and then actually inside the global memory, reconstruct the dense version of the matrix and run the computation that way. So we got rid of the host to global memory transfer, but we are still paying a lot of memory bandwidth between the cache and the global memory. And okay, we fit it into a GPU, but the question is, can we push it further? Can we actually make it like practically faster based on the GPU architecture? For this, we will need to go one layer deeper. And I guess all of you are doing a lot of machine learning, so it means that all of you are doing a lot of matrix multiplications. But I guess you have not done matrix multiplication by hand in a while, so let's like revisit this and how it's done. So we have two matrices, 4 by 4. We want to multiply them, and we want to get the result that is also 4 by 4 matrix. To get one number in the output, we need to take the first row of the first matrix, first column of the second matrix, and then gradually go one by one. So first, 4 by 3 is 12, plus 1 by 1 is 13, plus 3 by 1 is 16, plus 3 times 0, 16. Hooray, we have a first number there. But there's 15 more numbers to go, and it would take me quite a while to finish this computation. But luckily, I have a full room of eager processors that can perform this computation. So let's do an experiment. Let's actually finish this computation. So I want every one of you to choose a random location in the output. If you don't believe in yourself in choosing random numbers, just take your date of birth and modulo it by 4. Like the month modulo by 4, day modulo by 4, and you get the position. So I hope everybody has their position. And now let's try to actually compute it. When you will have the result, just shout the position and shout the number. Yeah, 212, I heard. Yeah, somebody understood the format. So not good at matrix multiplication at all, damn. Okay, never mind. Anyways, we could theoretically get the result with some computers and whatnot. But yeah, so this is the operation that is like the core of machine learning. How does it work on GPUs? Or what do we need to deal with when we run it on GPUs? There's like 3 for loops. Like, what could be the problem? To understand this, we will need to go deeper into some quirks of GPU architecture. First interesting quirk is that the streaming multiprocessors can actually execute 32 threads in parallel. And that sounds amazing. However, there is a catch, that this execution is in a mode called SIMD, or same instruction multiple threads. And all of these threads need to perform the same instruction at any given time. Maybe on a different data, but it needs to be same instruction. What is the consequence of this? Is that if you have if statements and you have some branching logic, these if statements will be much slower than you would expect. Because what happens is all the threads need to perform the same operations. So all threads will actually visit both of the branches. And if you want first 16 threads to do some stuff and next 16 threads to do other stuff, actually all threads will be in the first branch, but only the first 16 will be executing and the next 16 will be sleeping, while then all of them will move to the second branch and it changes accordingly. And you can kind of already see that this could be a problem for sparse matrices, because different threads could have different amount of work to do, but because they still need to execute the same instructions, you are pretty much always waiting for the slowest thread or for the thread with the most stuff to do. Second interesting property of GPUs is how it handles memory access. So again, imagine we have a streaming multiprocessor with 32 threads, and it accesses memory somehow randomly. And you could ask, like, okay, what's the problem? Just access the memory, all is well. Well, the problem is that the GPU can only communicate with the global memory in 128-byte transactions. And all these random accesses needs to be covered by those transactions. In this example, this random access triggers 3 different memory transactions, and most of the data will not be used at all, and we will need to wait for memory for no particular reason. The optimal way, or the optimal data access pattern for GPUs, is with all the threads are accessing sequential memory addresses. So for example, here, all the arrows are pointing to a very similar region, and this whole region can be served by only one memory transaction. So this access pattern is like much faster. And you may ask, like, what the hell, why is this important? Who is accessing memory in random locations? Well, it does not need to be random. It's enough that the memory access is far enough. And in the case we see before, it may happen that your threads need to access one column of a matrix, and all threads are accessing different elements of it. Unfortunately, this is not overlapping, so what ends up happening is that each one of these accesses will result in a separate memory transaction. And all of a sudden, you are fetching the whole matrix without you actually needing the whole matrix and wasting 75% of the throughput. How is this solved in practice? So we still want to compute A times B, but we want to somehow make the memory access better. Well, we can just transpose B and stall this version of the matrix. Interestingly enough, this is exactly what PyTorch does in their linear layers. It's storing the transpositions of the weight matrices, and if you always wondered why, well, this is why. And what it does is that our SM now needs to fetch data, so it fetches the row from A and the row from B transposed. But now this memory access is very nice and can be handled with only 2 memory transactions. So every thread gets the correct data, computes the output, and then the threads collaborate in an efficient way in log time to figure out the final sum, 16, and store the result. Unfortunately, the situation is much more complicated, and if you just implement this fix, it will only get you to like 12% of the optimal performance of the state-of-the-art matrix multiplication that you can get. So there is like still a long way to go, but limited time for this talk. Okay. What does it mean for sparse matrices? We still have not really solved the problem of like how to use them properly. So let's talk about that. This is a sparse matrix in a dense format. We have 16 elements, half of them are zeros, and it takes 32 bytes in our memory. The most popular format for sparse matrices is compressed sparse column or compressed sparse row. And it works something like this. We store an array of non-zero values, taking 16 bytes. And then for each value, we also store the column, the row index of this value. And for each column, we store the number of elements that column has and compute the cumulative sum of that. The problem of this format is that at sparsity 50%, it doesn't save us anything. And actually, the indices are taking much more space than the value themselves. So even though we prune the matrix, the size on disk is all of a sudden 50% larger than what we started with. So like, why the hell did we do the pruning? Other format that you could use is called bitmask. And what it does is that you take the original positions in the original matrix, and for each position, you just remember 1 bit, whether the number is present or not. And again, you store a sequence of non-zero values. And this format has a very good compression because the sparsity is encoded in only 2 bytes. So we really saved all of memory. Unfortunately, there is no public implementation of matrix multiplication using this format. And as you can imagine, it violates all the things that GPUs like. Like the memory access is scattered, the work is not distributed equally, like everything is wrong. But the compression is good. So if you just want to fit the model into memory, like this is perfect. And reconstructing the dense matrix can be done reasonably easily. So what is happening there? Let's look at some benchmarks or some baselines. This is a dense matrix multiplication as a base. If you would need to load the matrix from host memory instead of a GPU, you would get a 0.3x speed up, or like 30% speed. If you would look at like information theory optimal way what you could achieve in hardware that does not exist and in perfect compression, which is called speed of light analysis, you could at density 30% get 2.75x speed up. If you look at current state of the art for matrix vector multiplication at 30% space density, the speed up is around 1.18, which is, I mean, almost nothing, kind of negligible. And I'm happy to tell you that based on some soon to be published research, I hope, we have an interesting algorithm that can actually, for 30% sparsity, or sorry, for 30% density, give you speed up that's very close to the theoretical optimal. And we can get to like 2.3 to 2.5x speed up. I really hoped I would be able to talk about the algorithm itself much more, but unfortunately I can only show you the graph results and what it does, or how well it does it. So at this graph, we see some runtime for matrix multiplication at different sparsity levels. And we see a bunch of baselines. The blue line is dense representation. And what we see here is that sparse matrix formats only make sense at very high densities, at very high sparsities. So you need sparsity about 65% for the sparse format to even make sense. And recently we were able to develop a method called mutually aligned compressed coordinate kernel optimized sparse vector multiplication, very conveniently abbreviated to Macko. Oh no, GPT couldn't. GPT couldn't help with this, unfortunately, but yeah, it took a while. And we can expect this type of speed up. So all of a sudden, we have a sparsity that's viable at like 25% sparsity, which was almost deemed to be like not feasible at all, and quite a large region of improvement over the previous baselines. Okay, these are some numerical results and whatnot. Let's see how the compression works in practice for like a very practical case. So recently we had a client, Keyless, that works in a biometric authentication field, and it provides an authentication SDKs for mobile phones, internet banking apps, universities, and similar industries. Of course, they are running machine learning and they are running their AI model on the phone. However, they have a very strong limit from Google Play Store, and they want the app to be as small as possible. So preferably under 200 megabytes. Because the app contains other stuff, they want their AI model to be under 10 megabytes. Well, unfortunately, the AI model has 120 megabytes, so that's quite off the mark. And the question is, what to do about it? They did the sensible thing and applied off-the-shelf 8-bit quantization and received 30 megabyte model. However, if you take this artifact and you try to compress it with zip or other compression methods, you will get no compression at all because this is already as compressed as it gets. So what now? Well, that's when we came in. And this is what we did. So these are the weights in int 8. What we did is that we applied more aggressive 4-bit quantization and removed half of the bits from the thing. Important distinction is that this causes no memory reduction at all because there are still zeros, and we cannot expect the hardware to support int4 on random phone of random user. But anyways, we continued and applied 50% pruning to the network and set a lot of those weights to 0. Again, no memory reduction because those zeros are still there. However, there's a lot of zeros there. So if you take this model and you compress it, you will actually get a real memory reduction. And it's pretty easy to find a compression scheme that does it here. So in the end of the day, we were able to take a 120 megabyte base model, compress it down to 6.2 megabyte artifact. And this artifact is currently being used to authenticate people into their internet banking. And I'm kind of happy to announce that the company we did this for was very recently acquired, hopefully also because of this project. So if you are interested in deploying ML models, either LLMs or other stuff to mobile devices, or stuff with reduced capabilities, let me know, and I will be around. Thank you.
Thank you, Vladimír. Please stay with us. We'll continue with the Q&A, and I'll ask Standa to step up. And we will continue with the questions. So if you have any questions, just join Slido at hashtag better_AI, and you can ask anything. And also you can ask in person. We have a hand mic, so just wait for it until we come to you, because we want the streamers to hear you. So, and we of course prefer people live questions, and I've already seen one hand there. So let's start with the guys. Thank you guys for your presentations, by the way. It was really interesting. So I'm looking forward to the questions. I've already seen some on Slido. Yes, please.
Good question. Yeah, that's the main thing I'm trying to, the paper I'm about to publish discloses the method. But it, no, so that's on that level I can certainly answer in quite a detail. So the attack, the Stephen Hawking to Rickroll thing you've seen there, it's funny, and maybe I should have produced more examples of this, but it's very versatile. It doesn't have to be Stephen Hawking to Rickroll. Obviously, it's a very specific tuple of source and target, but that image was generated without ever talking to any of the GPT-5s or Claudes or Geminis or anything. It's a zero-shot transfer, so it is generated, and then immediately it works on the target model without ever being tested against the model itself. So this procedure is not leveraging interaction with the model. It's not like actually trying to wiggle its way into the model's kind of blind spot. It's literally working immediately after being developed on a very small surrogate model running on my small GPU, small enough to run on a consumer GPU here on its own. So I take a very tiny model, and with a pretty clever technique, but nothing kind of groundbreaking, I'm able to develop images that immediately zero-shot transfer to all the big models out there, including the GPT-5s and Geminis. And then every time a new model comes out, I'm like, okay, maybe it doesn't work anymore. And then I think actually one of the people in the audience tried right now taking a photo of the photo of the photo, and GPT-5 also got confused about it. So it seems to be working still. I think it's 5.1, probably already in the app. Was it Gemini? Okay, even better. So even a different class of models. And then you must consider that Gemini has a different image encoder than GPT-5, has a different image encoder than Claude, and again, different from the Mistrals and all the open source stack models, and yet all of them are fooled by the very same thing, showing that fundamentally some shared mistake is being propagated either from the data or the training procedure or the misspecification of the training objective. So something shared between the models is causing all of them to be susceptible to the very same attack. And the fact that I can do this without ever touching the model itself is, to me, miraculous, but pointing to a very deep, fundamental problem with the model.
Yeah, it sounds very impressive. Thank you. And it sounds really like magic. I cannot believe.
Thank you for the question. I would also like the video editors just to let the Slido questions here so that we can see them at the monitor. But we can do. Yeah, we have another one. Yes.
Yes, a question for Stanislav Fort about the text attack. In which condition do you have access to the vectors when you want to embed an attack in the...
So I had to be really fast in that part, but thank you. This is a very reasonable and that's the right question to ask for sure. So in that paper I was showing, it was artificially created in a way that I could touch the actual activation of the embedded word. And I was measuring kind of the security profile of these models by counting how many bits I need to control on the input in order to influence a single bit on the output. I was trying to kind of measure the susceptibility of the model, and the amount of attack kind of surface that gets translated into the damage on the far end. And I was measuring this kind of quantity, and I found out that it's very constant between models. And then now to your question specifically, playing with the activation itself is in a very unnatural scenario, except when you do retrieval, for example, with a model like Retro from DeepMind, that retrieves documents and admixes the embedded high-dimensional vector of that embedding into the embedding itself. So there you kind of have indirect access to the thing as well, or anything multimodal. Because in multimodal settings, such as image text models, the image that comes in, its projection from the image encoder is a high-dimensional vector. It gets added to the text activations themselves. So in that sense, you get access to the high-dimensional representation. But luckily, you can swap a token for a token in this discrete way, like for a cat or whatever. And in that paper, we actually find that it's as powerful as playing with the activations, as long as you understand that the dimensionality of the input you're playing with, because the tokens are from fewer choices, so fewer dimensions to your, at your disposal. But if you kind of account for that, it's like as powerful as playing with the activation itself. So TLDR, it's not a natural way to play with it directly, but through multimodal inputs you can. And the result applies to modifying tokens directly, which is accessible even through API, because you send text in, get text back. So it's the thing I showed is unrealistic in a sense, but it translates directly to a realistic attack scenario. Thank you. Good question.
Thank you for the question and for the answer as well. We have another one. Yeah.
One more. So first of all, I would like to comment on you should educate people in China so they can fuck up with their government this way. That would be like very helpful, I think. And question for GPU. You mentioned that the bottleneck is the memory size, but isn't it more like the speed of data transfer between these layers, or is it the size, or just dummy question because I'm like not an expert?
It's kind of an interaction of those two. Like, in a way, because the bandwidth between the GPU memory and the host memory is much smaller, much slower, then you need to use the GPU bandwidth as much as possible. So in theory, if you could have very, very fast connection between the GPU memory and the host memory, like you would not need the GPU memory at all, in a way. And it's to some extent what the DGX try to do, right? They have this unified GPU memory, which is just, well, RAM, but they're connecting it through the caches. So it's kind of interaction of these two. If we would have fast memory connections, we would not need GPU memory. But we don't, so we need as big GPU memory as possible. And that is actually kind of a problem, because it turns out that the complexity of your hardware scales exponentially with the size of the memory. So it looks like we are kind of reaching the limits of how big the GPU memories are going to get.
Okay, thank you. Stan.
Can I ask you a question?
Yeah, sure.
So when you were saying you want to move the 26 gigabytes to the GPU, wouldn't that happen only once at the beginning when you're loading the weights?
Yeah, that would happen only once. But that's the reason why you want to fit it into the GPU memory, right? But then you are paying the memory bandwidth between the GPU memory and the actual processor doing the computation.
But you were saying like how much it'll take per token, but like once it's there, shouldn't it be faster?
I already assumed that it's there, right?
I see.
If it would not be there, it would be actually 4 times slower.
Okay, makes
so
sense.
in the end of the day, the left one would get like 15 tokens, and the second one would get like 2 tokens.
Cool, thanks.
So you don't even want to.
Nice, thank you.
Like that's a word you don't even want to touch, not even like put on the slides.
Cool, thank you.
Yeah. Do we have some other questions? Oh, okay, great. Sorry, I don't see over the stand. So.
Okay. Hi, question to Stanislav. So the problem with the hues, so is that maybe solvable by like video recognition systems? Because like usually when you have like camera and you want to recognize something, right, you have like different light conditions and so on. So I would think like, you know, you would not break such a model like with just these hues, right?
That's a justifiable intuition, but it's not correct. And so let me tell you why it's not correct. You saw the images fooling the model under very different lighting conditions and orientations and obscurations. So taking a frame to a frame with small changes, each frame would be confused. You know, I showed you the Hawking thing, you know, under a tilt with a glare from a lamp on it, and yet the model was as confused as it was, you know, with a straight-on picture of the thing. So in some way, like having multiple versions of the thing might help. And it's an approach I used in one of the papers recently, in which we got some increases in robustness under such scenarios. But it's not an immediate, you know, solution for sure. This is an interesting field, kind of like on the meta level, because so many things seem like obvious solutions that, you know, there are literally 10,000 papers written on this, and the dynamic is very funny because someone comes up with a defense, they don't evaluate correctly whether it's kind of like breakable or not, and a day later, a paper comes in saying, "Hey, we broke the defense," and like back and forth for the past decade with very little progress in total. And so it's a very interestingly shaped problem because it's enough to have like very few kind of edge cases where this fails, and you kind of have to make sure like none of such edge cases exist for the thing to kind of be actually robust. So it's not enough to be kind of robust on average. It's not enough to be like robust in a typical scenario. You have to be robust under an attack from a you know, motivated, smart attacker trying to wiggle their way into finding the one place where you fail. So it's a very different scenario than you have to like the minimum of your performance has to be like as high as possible, not the mean, but you know, the min.
I just have to say that, you know, I like about this community that everybody is like immediately designing adversarial attacks. So this is really cool.
Yeah. Yes, for sure.
There's this trend in academia that people are using like LLMs for reviewing papers, for example. And I was wondering if this hue trick could be used for text as well. Like in text, you have this problem that you cannot change the token as much, but you have this lovely section called related to literature and all the citations that nobody really reads. So could you like shove some tokens there and all of a sudden your paper is...
Totally this works, yeah. Yeah, and also it's funny for my papers because when I use LLMs to review my papers to make sure I can like make them as good as possible, and I speak about these things and like the pictures in that paper describe these illusions for LLMs. The LLMs are like really confused what they're looking at in the figures, right? Like when I write a paper on this and the LLM is supposed to judge the quality, it like doesn't know what it's looking at when it's like reviewing the paper itself. Interesting times.
Yeah, I also wanted to mention that, you know, that the papers are usually better when they have pictures, and pictures can have adversarial attacks. So, you know, there's a whole space to explore in academia. So let's do that.
And this goes beyond pictures, by the way. Like audio is also a great way to sneak in information into these models.
Wow. Okay,
I have one more question for Stanislav. As I was looking at the attack that you added to the pictures, I was wondering if you have measured some, how far is it from white noise? So, well, if there is some lower bound of minimal information you have to add to the picture or to the token. Yes.
Yep. Great question. Measuring the differences between images is, you know, there's like a bunch of metrics. One of them could be L infinity norm, which is like looking at a maximum difference per pixel between the original color and the new color. And then in adversarial attack literature, there's like a classical kind of bound people chose, which is 8 out of 255. So, you know, a color in an 8-bit image goes from 0 to 255. The maximum change you can apply under these kind of typical settings is like 8 out of the 255, which was the change you saw in the dog to a car at the beginning. So very imperceptible. The Hawking thing was bigger. But you know, this very naive metric of choosing like the per pixel difference measures doesn't really capture the actual like semantic change to a human. And capturing that typically is done using a machine learning model. But you know, these things are designed to like not work for that metric, right? Like this small perturbation produces a huge diversion divergence in the answer from the machine learning model, which is normally the metric we use for like human understandable semantic difference. So this is basically impossible to measure in the original way, where you use an ML model to kind of quantify the difference, because here it's designed specifically to break that metric. So it's a bit of a cat and a mouse situation here. But in terms of the classical metrics like L infinity or L2, these are very small perturbations. You can go to very tiny perturbations. The one you saw with the traffic light was 4 out of 255, so extremely tiny. Basically, you could like a speck of dust could land on your screen, and it would be a bigger change in color than this.
Thank you.
Yep.
Okay, we have another one here.
Thank you. Question for Stan as well. So do you actually understand why this works? Like, why humans are not fooled and the LLMs are? Do we have a clue? Do you have a hypothesis why this works?
Yeah, as a blood reference to the $100 million question, yes.
It's probably
because
even
because
more.
you said you designed the attack, so probably you have an idea how it works, right?
I've got a ton of ideas. Whether they're correct or not, that's a different question. I think they've got a higher chance of being correct than a random idea, but I still wouldn't overclaim the probability. I think I've got some good intuitions about how to solve this. I actually have a grant right now to solve this. I did claim I can make a headway, so hopefully this is the case, knock on wood. But one interesting result from 2015 roughly is it pertains directly to the human visual system susceptibility. So you saw the cat, and it's or the dog, and it didn't look like a car to you at all, right? Like no intuition that it's a car in any way. But there was an interesting line of research back at Google Brain in 2015 roughly, where they kind of there's this like setup in neuroscience where you kind of clamp people's head in a setup to like kind of fixate on a particular picture, and you blink a picture on a screen in front of them for some limited amount of time and measure the response from the human. And they would have white noise, nothing there, and they would blink the picture of the attacked, let's say, dog that's supposed to look like a car to the machine learning model, to the human for like 40 to 60 milliseconds, and then noise again. And then they would ask the human what they saw. And it turns out, under this very brief exposure, humans are actually susceptible in a very similar way to the machine learning models. So something about a short-term human visual response is akin to the machine learning kind of seeing, but for some reason, looking longer negates this susceptibility. So something about the way humans process information visually over a longer period is kind of making them more robust against such attacks. And we know, like empirically, that there's a very similar kind of susceptibility, but weaker in humans also, but only for a brief exposure under very kind of like short windows, basically a single kind of frame in a video kind of exposure. This is a very interesting result, and no one followed up on that. And I think it's a very fundamental question. But since then, no other papers have explored this question. And but so we know, short-term vision in humans probably also susceptible. I would love to see if you guys, anyone here, like works on frogs or flies or kind of lower, in the tree of life visual systems, whether flies, for example, would be susceptible to these stimuli. Because they look at a very different way, and I'd like to see where in the evolutionary tree did the visual system become robust against such things. And if ever, right? Like that would be a really interesting paper, and I'm sure it would be in Nature if like done well. So if there's an academic in the audience, like please feel to pursue that, and you can acknowledge me in the acknowledgements. But I would love to see that result. I think it's a really exciting thing.
Thank you, super cool.
Can I have one short question?
So the fusion systems, when you really try to add the 3D LiDAR lasers and others, will also these 3D deep depth systems also be suppressed?
Yes.
Because the problem is that in these areas we are normally exploring, we understand them, but this fusion system is totally black box for us, even if we originally see them. So
you mean 3D?
Yeah.
So actually, this was like 5 years ago. I thought, okay, I know what the answer is. I'll model the 3D scene, and it'll work like magic, and that didn't work like magic in the end. So, the story is all this time in this little domain, these obvious ideas don't seem to be working, and if so, maybe multiple such ideas have to be combined to make them work. But certainly just putting the third dimension and depth in the picture and trying to reconstruct the scene is not sufficient for solving this. But good idea.
Thank you. I would just suggest let's now do a round of internet questions so that the guys on the stream have a chance to ask as well, and then we can return here. So let's start with the nice theoretical questions. What assumptions make you believe, Stano, that adversarial attacks for deep learning is either solvable or unsolvable problem?
Well, solvability is very clearly the case. You know, humans are not fooled, and we work in some way. Like there's an existence proof of a solution, and therefore it's solvable. So you know, I think it's a very clear answer. The same way I know AGI can be built because humans are AGI. So you know, I know there exists a architecture that does it. So obviously there is a way to do it. Whether we can figure it out like in a short amount of time or whether it'll be cheap, these kind of auxiliary questions, I don't know. But it certainly has a solution because nature found it. And nature isn't very good at finding solutions like that because it's a blind evolutionary search, very undirected. Like humans are way better at solving engineering problems than nature is. So I'm very confident we can crack it if nature could crack it.
Thank you. Does the noise have to resemble a specific image that should confuse the model, or do the adversarial attacks work with random noise as well?
No, that's the very specific thing. Random noise doesn't damage the perception of the model at all. They're extremely robust. You add a lot of kind of noise, you know, like white noise on top. It's barely recognizable to a human, and yet the model correctly classifies it as a cat or a dog or anything. It has to be a very specifically designed, crafted noise. A typical noise is like completely harmless, and it's even more harmful to a human than a machine. So that's the kind of conundrum here. These things are extremely robust and yet extremely brittle on the very specific attacks. So that's what confuses people about this. The robustness is huge, and you know, and unfortunately, this other thing I'm dealing with is also called robustness. So it's confusing in terms of the terminology, but robustness under average cases is a very different thing than robustness under motivated adversarial pressure.
Okay, and since I see you know a system here, because I think somebody is already developing either adversarial or adversarial attack. How would you compare adversarial attacks and defenses for images and text, or continuous space and discrete space?
Oh, I don't know. I think there are many techniques, and the techniques we employ right now are very insufficient. The way it's done, as a typical defense, is that whenever a thing works as an attack, you throw it back to the training set. You train on that and say, oh, you were wrong. This is actually a dog. It's not a car. But you have to do like 1 million versions per original data point to make this work. And so to make a tiny model that recognizes 32 by 32 pixel images into 10 classes, cat, dog, whatever, correctly, you need like GPT-4 level of compute to make that tiny toy model robust. So obviously nature doesn't spend that amount of compute to robustify the human visual system. So that implies that the approach we found in the 10 years of exploration is a bad approach. So that motivates me to find a new approach to this, because we know the current line of practical defenses that every major tech company employs to make their AI models, you know, as robust as possible. But you know, obviously it wasn't very robust under actual pressure. That's very unscalable. I worked on Gemini, and then there, one of the papers actually introduces a new technique, partially helping with robustness, and we got a patent for it as well. But it didn't solve the problem, you know, basically to any measurable degree.
Thank you. And we are still designing the adversarial models. So I think we already showed that the same physical adversarial examples work for different combinations of cameras. What if we try to use a screen and not paper for attack?
Yeah, I think we just tried this here. Like Adam, you know, one of the people in the audience, my friend, he actually did it just now, right?
I just took a photo of the projection screen with the photo of the photo, and I put it in the current Gemini Pro, and it was still fooled.
Yeah, I would actually like to ask the guys who are watching the stream whether they have seen his photo and whether they try to replicate we would do like the full Inception, you know, level adversarial attack. That would be like really fun.
If it fails, just remember it did work just now. No guarantees.
Yeah, thank you. Thank you for all the participation, by the way. This is like really fun. To Vladimír, finally, what is the final RAM footprint of the model for your bio-authentication?
Yeah, so for this case, we were only interested in making the artifact as small as possible. So what we did there is, it was just the size of the zip. And in the end of the day, it was just decompressed to the original 8-bit size, so it was 30 megabytes. However, what you can do is that you can take the model and take the artifact and let it be zipped even inside the RAM and do the decompression inside it. Like you will pay for it with some speed degradation, but it may be feasible to do so. It really depends on what you want to do as a trade-off between memory and CPU and hardware that you have. But if you would really like to get the proper speed up, as I shown on the last graph, unfortunately you need to write like custom kernels or custom code to run it. And if you deploy across wide variety of mobile phones, it could be tricky. If you only deploy to like iPhones, then it could be much, much, much simpler.
Wow, thank you. Yes?
Can I ask you a question? So Perplexity was on some typical like training set. Downstream performance on specific metrics might kind of not be captured by the Perplexity, dipping only a little bit. Do you know whether kind of you heard like reasoning more than the generic, like train set performance?
Yeah. So for example, we tested on stuff like zero-shot question answering, and there the degradation was a few percent.
I see.
Like it was consistent with what you would see based on the Perplexity. There the trick becomes a bit more interesting because if you are only interested in performance on some specific task, you can tailor your compression to that specific task. We have not done this yet, but that's what we hope to kind of achieve there. That if you are only interested in, I don't know, making good English grammar checking models, then you can probably compress the hell out of the model and still be okay with it.
Thank you. And I will continue with a question for Vladimír. What do you expect for the future of LLM compression, both for consumers and for businesses downscaling to smaller weight numbers?
So the future that I'm not sure if I see it, I hope I see it, and that I hope for, is that there will be much more control given to the hands of people and small businesses compared to what's happening nowadays, right? Because if you want to run those large-scale models, like, good luck with that. But if we are able to push for the compression, then all of a sudden you could have like pretty large model running on your desktop that is ingesting all of your life, and you don't really need to care about it because that model does not even need to be connected to the internet. And then from time to time, you just take the model, compress it, deploy it to your phone, and all of a sudden you have like your personal assistant that has all the capabilities of a large LLM, but it's tailored like specifically to you and running on whatever you want. So that's the one that I hope for.
And we are coming back to the adversarial attacks. And this is a question I actually had at the beginning as well. Do you see any adversarial examples in the wild? I mean, for security purposes?
Yes. In one domain that I'm not that familiar with, but I know many people in ISLE are, which is malware is often detected based on a signature, and there are attacks kind of modifying it specifically to bypass the malware detectors. So that's one. A related example is practical. Another example that I might point to is that bypassing. So maybe I'll stop here. I think some of the things are a bit sensitive, but it is practical, yes, and I've seen them in the wild being used as well.
Wow, this is quite interesting. And okay, what is the procedure of creating the noise for the attack? Are there any challenges for doing that?
It's very simple and cheap and fast, but it would take a longer time to explain, and I'll hopefully publish it very soon.
And yeah, there's a question of actually how you do it. Are you getting pixel-wise activations of the gradients on images A and B, which must overlap, and then transferring that using style transfer?
No. That's very complex, and I assume the images A and B must overlap. This sounds like a pretty convoluted way of doing it. It sounds plausible. It could work. I wouldn't like dismiss it immediately out of hand, but that seems like a very complex way of doing it. The standard way of doing it, by the way, is very trivial. You just the way you classify images is that you take the pixels in, push them through the model, and get the probabilities of the classes out. Then to train the model, you normally take gradients. That's kind of done for you by the autograd functionality, by PyTorch or TensorFlow or JAX or whatever you use. Now, what you can do is say, hey, how would I have to change the input pixel such that the probability of class dog goes up? And it says, oh, you have to like change this like pixel up and this pixel down. So you do that a little bit. Then the probability changes a little bit. And you're like, again, okay, so now how do I change the pixels in a way that the probability of dog goes up? And you do a few steps like that, and immediately the model is fooled. So originally people did that because they assumed if they kind of say, how do I change the pixels to make class dog go up? They would get a picture of a dog. But what they got instead was a picture of noise that the model confidently classified as dog. And now they thought, okay, this is some quirk of the model itself. But then they noticed the same picture shown to a different model, trained in different way, from different weights, initialized and everything, still confuses the model to see the target of this procedure. So it is kind of dog to the models, and transfers between them is reliably a dog, and yet it doesn't look like a dog to a human. So originally the motivation was to build generators, not attack models. But this failed, and we got a new 10-year long-standing problem out of it. Christian Segedé, the guy who was on the original paper, he was a co-founder of X.AI with Elon Musk. Recently, he launched a startup solving proof building with LLMs, a very successful mathematician. He's the guy who kind of told me this backstory. He said, originally we wanted to build a generator. Actually, we got this attack. It's very interesting, but kind of a disappointing end to the whole thing because we hoped we would make pictures of dogs instead.
Okay, thank you. And let's do the one last question that we have here on Slido, and then we will finish. And you can talk in the background later. So, what makes you think that instead of thinking about it as a neural network is confused by the adversarial attack, actually our visual thinking is confused?
Good question, but it's a matter of semantics. And here, truth I define as what I perceive. But if you kind of did define it as the model's response, then obviously humans are defective. But I would say that given the evolutionary pressure to like do well at seeing dogs correctly because they could bite us otherwise, and when we perceive the world, there are consequences to that perception being wrong. And I think that likely produced a faithful perception on our end. Obviously, the visual illusions exist, so we do not work perfectly. But I would wager humans here are more robust just because of the 4 billion years of evolutionary pressure to develop a reliable way of perceiving dogs and things like that in the physical world. So my bet is on the humans, but this is a matter of semantics, and I just choose axiomatically that humans are the ground truth here. But good question.
And we still have, sorry, but there's still one question, and I think it's interesting. Do you think it's possible that the transferability of the attack is due to the models being trained on the same data?
Good idea, but not the case. Here, this was one of the original thoughts that people had. It's interesting to see the audience recapping the history of this field, but this is not the case. The models are very much not trained on the same data. The model architectures are very different. The Gemini encoder, the Claude encoder, the GPT encoder, the Mistral encoder, like as long as I know what they are different. They are trained on different data. They have different architectures, and yet these things transfer. And so obviously, it's not the same architecture. It's not the same data. It's not the same initialization of the weights. It cannot be that. It could be something about the underlying reality they're perceiving and the way they're learning how to detect things. But it's not something as naive as literally the same pictures in the data set. But good question.
Thank you very much, Standa and Vladimír. Are there any final questions here?
One last question from the audience here. Nobody?
Okay.
Okay.
All the questions are exhausted. This is nice.
Oh, there's one.
Oh, is it?
Here we go. I knew it.
Okay, great.
So would that actually connect to one of the thoughts that Vladimír mentioned in the beginning of his presentation, which was that the weights within a neural net usually have some kind of a sort of tail end of the distribution where the weights are much more important than the others. And so you could get some of the sort of similar connections across different architectures where you sort of get a similar structure that gets activated by that kind of noise.
Oh, who are you asking?
So I was asking you, Stanislav, but I was just trying to sort of connect the two presentations in some sense, where sort of continuing off of the last question that you had.
If I get you correctly, weights have long tails of rare but like super important weights. You're saying maybe in like the visual stimuli, there's like a long tail of like very important visual stimuli that.
Yeah. So despite models being trained on the same on different data, as they learn, they sort of reconstruct similar activation networks, and so that's perhaps what you're capturing with the adversarial attacks.
You're correct. Like they have to have a large amount of similarity, because if I show a real picture of a real dog to the networks, they all agree it's a dog. So in that sense, they're all kind of the same. Their response, on the normal stuff is the same. So in a way, it's not that surprising they might agree on this noise-like pattern, except it's different from the humans that used to agree on the normal dogs, and now they disagree. So there's some departure. And humans seem to be trained on the same data as these models, also pictures of dogs, also pictures of houses and whatever. And yet the solution we get seems to be radically different from the machine solutions here, but radically different from the whole group of the machine solutions that seem to be similar in that. So whatever it is, you might be hinting at some underlying structure they're learning, but why that structure is different from the structure humans learn is the key question here.
All right, thank you.
Thank you. Okay, thank you. Thank you very much. I think this is really all for now. I have to thank the Czech and Slovak audience for active participation. This was like really fun.
Amazing, thank you so much. Not only Czech and Slovak, there are other nationalities in the room as well. So
that's why we talk English, because we we invite everyone. Thank you first and foremost to Prague AI. It was great being here. This is such a great place. We hope to be here more often. So this was really fun. Thank you for those who came here to actually celebrate in person the triple anniversary that we are currently having. And let's say we have to thank also Slovaks AI and LoRa AI for making this happen and for supporting us. And this was a really true Czecho-Slovak spirit, I have to say. And speaking of spirits, because we are at the end of the long party, actually, so you're all invited who are in person. And of course, to those who are watching the streams, we are, never gonna give you up and never gonna let you down. So stay with us and see you soon. Thank you, everyone. Goodbye.
Thank you.